Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillahirrahmanirrahim. Welcome back. Problem 8.1. So in this problem, it is given that a W10 by 39 rolled beam supports a load P as shown. So you can see this is a beam AD and it supports a point load at point B and C. Clear? Knowing that P is equal to 45 kips, A is also given, that is 10 inch. This distance is from B to C is 10 feet. Clear? And allowable stress is 18 ksi. So determine the maximum value of normal stress sigma m in the beam. The part B is maximum value of principal stress at the junction of flange and web, and C part is specified shape is acceptable or not. Clear? So let's start with the given data. So it is given that this is W10 by 39 rolled steel beam. Also the value of P is given. P is equal to 45 kips. Clear? Distance, this small distance A is equal to 10 inch. Clear? And length of BC is equal to 10 feet. So I will convert it into inch. So 10 into 12 inch, which is equal to 120 inch. Clear? Allowable stress is also given, that as 18 ksi. And what we have to find, so the first part is that you have to find the sigma max for the beam, for whole beam, for beam. In part B, it is asked to find the maximum value of principal stress sigma max at the junction of the flange and web. So principal stress, that is sigma max, or you can say sigma 1 at junction of flange and web. So if I draw the cross section of this I beam or W, so you can see this portion is known as flange and this portion is known as web. Clear? So this is the junction. This is the junction. So you have to find the principal stress at this junction. And the third part is that whether specified shape is acceptable or not. So this is all about problem. So let's start with the solution. So you can see this problem. For solving this problem, first of all, you have to find the reaction force at support A and D. So for finding reaction forces, at A and D, we will draw the free body diagram and we will find out the reaction forces. So let's say this is the beam. Clear? At point A there will be a reaction force, that will be RA. So at this point there is a concentrated load. Similarly at point D there is also a support. Clear? So this will be RD, and again there will be a P force. So this distance is given as A, which is equal to 10 inch. Clear? And this is also 10 inch. And this distance is from this point to this point, this is 120 inch. So this is point B, this is point C. So by using equilibrium condition, you can find these forces. Sum of all forces along y direction is equal to 0. So you can see there is upward force reaction which is Ra minus P, this one, plus Rd is equal to 0. So it means that Ra plus Rd is equal to 2P. So we have won this equation. Now we will apply the second condition of equilibrium, that sum of all moment about any point. So we will take point B. So sum of all moment about point B is equal to 0. So you can see here at point B, this reaction force is producing moment in clockwise. Clear? So it will be Ra into 10. And that will be negative because it is clockwise. Similarly, movement due to this load at point B, which is minus P into perpendicular distance 120 inch. And again, this is producing clockwise, so it will be negative. And this force which is producing movement about point B, and that will be equal to plus Rd into perpendicular distance is 120 plus 10, which is 130. Their sum must be equal to 0. Now if you further simplify it, this will be equal to 10 minus 10 Ra, clear, minus 120 P plus 130 Rd is equal to 0. Clear? So you can see it is also in term of Ra and Rd. So from here you can also convert Ra is equal to 2P minus Rd. So you can put the value of Ra in this equation. So when you put this minus 10 into 2P minus Rd minus 120 P plus 130 Rd is equal to 0. So it will be minus 20 P minus plus 10 Rd is equal to minus 120 P plus 130 Rd is equal to 0. So this minus 20p minus 120p, it will be minus 140p plus 140 Rd will be equal to 0. So implies that Rd will be equal to P. Clear? So when Rd is equal to P, clear? So you can put here as Rd is P, so it will be again equal to Ra will again equal to P. Clear? And you know the value of P, which is equal to 45 KSI. So this is how we find the reaction forces. Now we will move toward our first part, that is you have to find the maximum stress for the beam. And we know that for maximum stress we have formula that is equal to maximum moment divided by section modulus, which is S. Clear? Or you can write as Sx. Clear? So what we will do is that we will find the maximum moment for this beam. For that we will have to draw the shear force and bending moment. So I will quickly draw it. This is the beam. You can see the beam with the loading shown. This is now Ra, which is equal to P. This is again, this point load is P. This point load is P. And this Rd is again P. So you can easily draw the shear force and bending moment diagram. The length is given, Clear? So if I roughly draw it, the shear force and bending moment, clear? So let's say this is shear force, this point is 0, so you can see at this point this will be P, and let this point is plus 45. So again this is 45, and up till this point if I project, this will be the same load, and here this is plus 45 and this is minus 45, which will give you 0. Now you can see here there is no load, so again this the shear force will be 0. Now at this point you can see the load is minus P, which is minus 45. So minus 45 will be this one. Here, this. So this is your shear force diagram. So you can see maximum, from here you can find out the maximum shear force. The mod of maximum shear force is 45 kips. Clear? Now we will move toward finding the bending moment diagram. So you can see here from this point to this point, this is the shear force. Clear? And the area under this diagram will give you the moment. So this is 45 and this distance is 10 inch. Clear? So 45 into 10 will be 450. So you have to plot as per your scale. You have to draw the shear force and bending moment as per scale. Now you have a proper knowledge and you can easily do it. So let's say this point is 450. Clear? So you can draw, as this is a linear, constant line, so the shear bending moment will be a linear line. So it will be like this. Clear? Now here there is no shear force, so it will be a flat. And again here this area will be minus 450 and it will be again come back to 0. Why? Because this line is negative minus 45 and the bending moment will be decreasing. Here it will comes to this point. So this is bending moment. So from here you can find that maximum bending moment is 450 kips into inch. Clear? Now you have maximum bending moment, so you can put it in the formula, which is equal to sigma max is equal to maximum bending moment. Maximum bending moment divided by section modulus. Now we do not have section modulus, and it is also given that this is W10 by 39 rolled shape steel beam. So we will go to the appendix C of this book, Mechanics of Material by Baer and Johnston. So you can find out its properties. Now you can see I have highlighted the W10 by 39. So you can take the value of these properties. You can see the height of beam is D, which is again 9.92 inch. The width of this flange is BF, which is again equal to 7.99 inch. All these values are given over here. You can see section modulus SX is 42.1. So I will write these value over here. I have also written it on separate page. So I will move toward that and will write this value over here. So for this W10 by 39 beam, I have D is equal to 9.92 inch. Clear? Breadth of flange BF is equal to 7.99 inch. Clear? Thickness of flange is equal to 0.53 inch. Clear? Thickness of web TW is equal to 0.315 inch. IX, second moment of inertia about x-axis is 209 inch for clear. SX, which is equal to 42.1 inch cube, clear. So all these values are given. I will also draw it here so you can easily understand it well. So this distance is, this is thickness of flange TF, which is 0.53. This total distance is the height of the beam, which is represented as D, clear, and this D is 9.92 inch, clear. This is web, clear, and the thickness of web TW is again 0.315 inch, and breadth of flange is 7.99. So this is breadth of flange. So all the values are given, and these values have been taken from this appendix C of this book, Mechanics of Material by Baer and Johnston. You can cross verify it. Now you can see that if I draw it again, this beam, clear. So this is the total, let's say this is total D, clear. So half of the D will be equal to its neutral axis, clear, and from neutral axis to the outermost surface it will be equal to C, and this C will be equal to 1 over 2 into D. So if you put the value of D 9.92 and divide it by 2, it will give you 4.96 inch. Similarly, this is the top of the flange. So if the junction of this flange, clear, or height of this point where this is the junction, so let's say this is point B, so this height will be equal to YB, and this YB is equal to C minus this thickness of flange. So this YB will be equal to C minus TF, thickness of flange. So 4.96 minus 0.53 will yield you 4.43 inch, clear. Now we know that for part A, maximum stress is equal to maximum bending moment, clear, divided by section modulus. So we have maximum bending moment, that is 450 kips into inch. So I will write 450 divided by section modulus, and that is 42.1 inch. So 42.1 inch. So that will give you the maximum stress for the beam, which is 10.69 KSI. Clear? So this is the stress that is at the top of the flange, clear, or you can say at the bottom of the flange. So this is the maximum bending stress. Now in part B, it is given to find out the principal stresses at the junction. At junction of flange and web. So for principal stresses, we know that this principal stresses sigma 1 or sigma 2 is equal to sigma average plus minus R, and you know that R is equal to sigma x plus sigma y divided by 2 whole square plus tau of xy whole square under the root. So here you will need the normal stress and shear stress at this junction point. So we will first calculate the normal stress at junction point. So normal stress at point B is equal to, at this point B, clear? So this will be equal to YB over C multiplied by the maximum stress. So you can see here YB is this distance divided by YC. So ratio of this distance into maximum stress that you have been calculated. So YB is 4.43 and C is 4.96 into 10.69 will give you the value of 9.55 KSI. So again the stress is reduced, normal stress is reduced at this point. Clear? So normal stress is maximum at the outermost surface. So if you come down toward the neutral axis, the normal stress will decrease, and you can see it is 9.55 at this point B. So sigma B here will be equal to 9.55 KSI. Now we will find the shear stress, and we know that shear stress at this junction XY will be equal to V max into Q divided by I into thickness. Clear? So we have V max, which is given over here, V max. Clear? We do not have Q, and Q is the first moment of inertia, and that is equal to area into YF dash. Now area of what? We will take the area of flange, because at the junction of web and flange we have this area. Clear? So area of flange is equal to breadth of flange into thickness of flange. So you have breadth and thickness as well. This is 7.99 into 0.53. So 7.99 into 0.53 inch. So it will give you the area of flange, that is 4.23 inch square. Now you have this area, so you can see that this area will lie, the axis of this area will be this one. So this distance is YF. YF dash, and this YF dash is equal to YB plus half of TF, So you have YB as well as and thickness, so you can put the value over here. This distance will be equal to 4.695 inch. Clear? So you have A and YF, you can put here to find Q. So A is 4.23 and YF is 4.695 inch. So when you multiply this, so the QB will be 19.88 inch cube. Now you have V max, you have Q, you have I, that is second moment of inertia, that 209, and you have, this will be the thickness of web, because we are going to find the shear stress at this junction. So shear stress will be like this. So thickness of web is also available. So you can put the value of XY is equal to 45. Maximum shear stress is 45. Clear? And this Q is equal to 19.88 divided by I is given as 209 inch 4, and thickness of web is 0.315. So if you calculate it, this shear force will be equal to 13.58 KSI. So now this is the scenario. At this junction we will be having a load that will be equal to shear force, that will be 13.58. Clear? And a normal stress that will be equal to 9.55. Clear? Let's say this is the normal stress, sigma B. So when you draw the Mohr circle for this R, for finding the principal stresses, we know that sigma 1 comma 2 is equal to sigma average plus minus R. So we will take the maximum value, that is sigma 1, and sigma 1 is sigma average plus R. As we know that only normal stress is sigma B, so average will be equal to sigma B over 2 plus R is sigma X plus sigma Y is divided by 2, and again it will be sigma B over 2 whole square plus tau of xy, and tau of xy is 13.58 whole square. So you can put the value sigma 1 is equal to sigma B is 9.55 divided by 2 plus 9.55 divided by 2 whole square plus 13.58 whole square. So when you calculate it, this sigma 1 is equal to 19.18 KSI. So this is the principal stress at the junction of flange and web. Clear? Again, in part C, it was given to check whether the specified beam is acceptable or not. So you can see that your principal stress should be less than the allowable stress. So we will check sigma 1 is equal to 19.18 KSI. Clear? While sigma allowable that is given in the question is 18 KSI. 18 KSI. So you can see your principal stresses here for safe specification. Clear? But you can see from the value that sigma 1 is greater than sigma allowable. Clear? Hence, what we conclude is that W10 by 39 is not acceptable. So this was all about problem 8.1. I hope you have learned and enjoyed this video, as well as you have now a sufficient knowledge about bending moment, shear force and all other. So it will be easier and interesting problem for you. Thank you for watching.